this computer. I'll record to my computer.
Okay.
There, okay. All right. So we're being recorded. Hopefully nobody's being shut off. My wife, aka my spouse unit, managed to uh break her toe.
Oh,
So
no,
she's
no.
not walking anywhere. We're not walking through any of the great celebrations at Tempe Town Lake or at or at uh
That's
Fountain Hills or anything like that. Instead, we're going to
mhm.
mostly just stay here and watch it all on TV while she has her foot elevated. So
Okay.
that's our story there. Krista, you've used Zoom before. You know how to share your screen in a moment.
Yes. Let
All
me
right.
do that.
I don't know who was going to introduce you, but I guess the default is me, unless somebody else volunteers or somebody else told us that they're going to present. Yeah. Okay. Good. Yeah. All right. Very good. And you're in slideshow mode and all that good stuff. Oh, good. All right. Looks like we have how many of us are showing up so far? Let's see if I got my little count here. We got seven us. We have six. Somebody just dropped off. Was it something I said? Okay, hopefully we'll have everybody on back momentarily. Now we're back to seven and popping upwards and onwards from there.
Eric, I also invited the Reliability Society group,
Yes,
so
yes.
there's some
Yeah, I think
popping
we're
up
joint.
here.
I think we're joint sponsoring it. So thank you, Christian.
Yeah, thank you, Chris. Yeah.
Yeah, because it is very much relevant with the reliably monitoring.
Correct.
All right,
That's
great.
what we're doing here.
All right. Okay, well, I guess with no further ado, other people will pop into existence, but the introduction is probably the least important. So I guess I'll try to quickly get the introduction out of the way, and that'll give more time for Krishna and for any questions that might come up. So, welcome, both the Reliably Society and the Engineering and Medicine and Biology Society of the Phoenix chapters. Um, we're going to be welcoming Krishna to give us a talk momentarily. So Krishna is an IEEE senior member, and he's also from an IEEE standpoint, an officer in the Engineering and Medicine and Biology Society Phoenix chapter. Um, Besides working as a senior principal IC design engineer, which he'll be giving some of his examples from momentarily. On the side, he's pursuing his doctorate in electrical engineering at ASU. So a lot of free time available for you. Yes, yes. Anyway,
Sure.
and he's going to be Christian is going to be sharing us today. Um, for medical devices that are implantable, I happen to have some with me. Try to show a little bit of electronics inside.
Awesome. Yeah.
So I have some examples here. I'll try to show it on my little camera over here. So Krista's involved in designing these integrated circuits that go into these implantable medical devices like um, pacemakers, defibrillators, neurostimulation units. And so Krista is a senior principal IC design engineer. You have to have these systems be very low power. So we're talking about ultra low power, mixed signal integrated circuits for implantable medical devices. And so that's the topic Krishna will be sharing with us today embedded mixed signal test and reliably monitoring in biomedical electronics for these implantable devices in particular. So with no further ado, take it away, Krishna.
Yeah. Thank you, Eric, for that elaborate introduction. I just have to add, I'm doing my doctorate with two toddlers, so
We're two
a lot
toddlers.
of fun. Yeah. So, and thank you all for joining today. Uh, First, I just have to mention that everything I will be discussing today will be based on publicly available information and research. So, if anyone is interested in exploring more, please feel free to dive in because I don't have time to cover everything in much detail. Okay, with that out of the way, let's dive into today's topic. Embedded. I hope you can see my screen because I have this bar on top.
Yes.
If I can hide this. Okay, I hope you can see. So, embedded mixed signal test and reliability monitoring. So, before a biomedical electronic system is released, we put a tremendous amount of effort into making sure it performs as intended. We characterize it, test it across various operating conditions, screen it for defects, calibrate it if needed, and verify the complete system. But for many long life biomedical systems, that is only the beginning, right? Once the device is deployed, the external test is gone, the access is limited, and the electronics may need to continue to operate for several years. So the question I want to explore today is simple. How do we know that the performance we verified at the beginning of life is still there later? I will approach that question from both mixed signal circuit and embedded test perspective. We will first look at how confidence is built before release. Then we will look at what changes over time, what becomes harder to observe, and how embedded test reliability monitoring, calibration, and diagnostic logging can help preserve that visibility. So let's start first by looking closely is what is actually means to preserve performance over the life. At the beginning of life, we have one major advantage, right? That is control. So we know the temperature we are at, we know the supply voltages, we know the operating modes, um, and also the stimulus we are going to apply, the load, and the measurement setup. Under those defined parameters, we can establish how the device performs and how much margin it has related to its established requirements. Now, let's fast forward several years. The system will still turn on. It may still complete some basic functional checks. It may still perform its primary task. But does it automatically mean that the original performance margin is still there? Uh, Take a few seconds so we can think about this and think about what additional evidence we might require. We might want to know whether if the leakage of the system has increased, whether the reference or the clock has drifted, whether a power delivery path now shows extra droop for a load event, whether the sensing path has more noise, offset, or gain errors, or whether the output path is still produces expected response under the given conditions. So we have three levels of confidence that we have to think about. One is the circuit still functional? Is it still within specification? And is it still behaving consistently with its verified beginning of life state? These are not the same things, right? A circuit can still work while its margin is shrinking. It can remain within specification while moving away from its original behavior. The circuit can still work while its margin is shrinking. It can that is the problem reliability monitoring is trying to address. Preserving enough evidence to know not only if the system still works, but the important performance and margin are being maintained is vital. Um, so we have to explore how difficult um, that becomes uh, based on the system constraints under which they operate. The same basic test techniques are applied or appear over all the biomedical systems I'm showing here. For example, the first one, the wearable monitor or the bedside system, a surgical platform, and the implantable devices may all use the same checks, calibration, reference monitoring, or current measurements, fault logging, or diagnostic signatures. So the techniques may be similar, but what changes is how critical the function is, how quickly a problem must be detected, and how easily the system can be accessed or serviced. A wearable monitor, for example, may be relatively easy to replace, while a bedside system may be regularly inspected, maintained, and calibrated. But even those systems, there are there health monitors that are embedded that can reveal the problem between these scheduled service intervals. And coming to critical features like surgical platforms, for example, they also might be very serviceable and may include extensive diagnostic. However, the consequences of fault during an active procedure can be much higher. In that situation, knowing that the system can be repaired later is not enough. The fault may be needed to be detected immediately, isolated quickly, and handled in a controlled way so that the system either continues safely or transitions into a defined safe state. And coming to the implantable systems, they also add another layer of difficulty. The function is highly critical and physical access is very limited. The device can often be interrogated. It can store diagnostic information. It may communicate through telemetry, but it's not available for the same direct measurement we can perform with an external system. So across all these applications, um, three questions keep changing. How serious is the consequence of failure, and how quickly must a failure be detected, and how much access do we have to diagnose or correct it? So for the rest of the talk, I will focus mainly on the implantable systems because that's my focus area, and also because they combine high criticality, limited access, and severe resource constraints to the extreme. Once we move to the implantable environment, every additional measurement comes with a trade-off. Um, so coming to the implantable system constraints, there is a central tension. We would like to see more information about how the electronics are performing, but we have very few resources available to collect that information. So the physical access first is limited, and the energy budget is extremely limited. Uh, for example, if it's a primary self device, every additional measurement or a wake up event or a communication session consumes energy that would otherwise support useful device life. If it's a rechargeable device, it has a different energy model, but the trade off does not disappear. Additional activity can still recharge frequency. Uh, additional activity can still affect recharge frequency or efficiency, even battery aging and long-term availability. And also, we have to remember the memory on board is limited, communication bandwidth is limited, and many of the most important functions are operating as mixed signal. The system may depend on a few low noise sensing paths, stable references. It needs accurate timing. The data conversion should not drift. The power management should perform. The therapy control and protection circuitry all should come together. The electronics um, also move through several life cycle conditions. These can include like storage, handling, transportation, and implantation, of course, and then it has to survive for a long time in the human body. And if something abnormal occurs, simply detecting it is might not be enough. The system needs a defined response. That response may preserve an essential function and inhibit an unsafe output and enter into a fallback state. And also, it is supposed to record the event and communicate the condition when possible. So the real question is not whether we can monitor everything. Obviously, we cannot. The question is which behavior uh, is more important and that we like to observe, and what is least intrusive um, when we try to observe it. So to answer that, we need to look closely at the architecture of these implantable devices and ask meaningful questions and think about what actually can be collected. So here I'm showing like a simplified architecture, which gives us an useful way to organize this problem, right? The main signal path here begins with that physiological input from the electrodes. That signal moves through the analog front end, then through the data conversion, and then there's a processing and decision logic. So if a therapy is required, the system then moves through the therapy control and the output and energy delivery stage. So supporting uh, the main path are the energy source, the power management, a voltage and current references, a few clocks and time and memory and telemetry and some protection logic near the electrodes. So each of these areas give us an opportunity for observation. So coming to the signal path, we may inject a small known stimulus and evaluate the response. And for the converters, we may check the gain, offset, or linearity related behaviors. In the power path, we may monitor current or impedance. We may verify the reference or clock if it remains within an expected range. We may also have some reset history, some stored events, and operating conditions to help explain what happened. This important point is that there's no single observation that tells us everything. So, for example, if we make a current measurement, it gives us one part of the story. but a reference check gives another, and a stored event gives us another uh, observation point. Together, they help us build a complete picture. But unlike the measurement we make before release, we no longer have the full access here because unfortunately the precision tester cannot be implanted with the device. So we have to be selective about what we observe and when we observe it and what conclusions we can reasonably draw from the result. So before we can be uh, before we look at what can be monitored, if we take a step back and we should observe like how the conference is built before we even reach a patient or in-field state. So before we start talking about the embedded self-test, it is worth asking a simple question. How do we establish confidence in a product before release, right? The answer is not one test at the end of life. Confidence is built usually gradually, with different activities contributing to different pieces of evidence. So during design, we'll define requirements, identify risks, establish some margins, and verify that the circuits behave correctly across expected operating conditions. And when we come to the qualification, we evaluate whether the design and manufacturing process can withstand some relevant stresses. And the production test then looks at individual units and screens for defects and looks for parametric outliers. Then we have calibration that manages any source of this variation that we observed. And the system level verification at the end will confirm that the complete product comes together, not just the individual circuit block, but just the complete system behaves as intended. These activities are all related, but they're not interchangeable. A design stimulation, like a design simulation, cannot tell us whether the product manufacturing can actually contains a defect. A production test cannot replace the system level verification. That is why confidence is here is built in layers. So each stage evaluates a device at a different condition and answers a different question. And embedded monitoring should fit in to that same philosophy. It does not replace the existing assurance. Uh, it carries like a selected part of that visibility forward after the external equipment is not no longer available to test our parts. And whether this visibility exists later depends on the decisions we make much earlier during the architecture and design phase, not later. Um, when we looking for designing for reliability, so reliability should start before the first test even happens. So when we think about test, it is easy to picture that it's a measurement that's performed after the circuit has already been designed. But in many cases, the important testations happen much earlier. It happens when the architecture is actually defined. The requirements and risk analysis tell us what must be verified, what must be protected, and what behavior must be useful to monitor. The architecture then determines whether that information will actually be available. So the question we should ask during the design phase is, can we access the internal nodes we care about? Can we apply a known stimulus? Can we measure a response with enough accuracy to make the results useful? Um, can we isolate a block from another? And can we distinguish a local circuit change from a system level artifact? So these difficult questions to solve after design is complete is really tough. So the calibration paths need to be planned much early. All the protection circuits needed to be placed um, before even we hit the field. All the fault response behaviors must be planned for any abnormal conditions that occur. And if we want to store any useful diagnostic information for evidence later, the system needs a way to capture and preserve it. So the testability is not something added after the design is finished. It is part of designing the system for reliable operation. That includes designing for conditions outside our normal operation. The device may encounter a sudden electrical transient or a clinical interference or like an MRI event or an extreme temperature change. The response to the conditions must be improvised they cannot be improvised after the product is built. It has to be designed when the system is built and then verified. So this visual is showing some examples of conditions that require more than ordinary normal testing. Uh, they are different problems, but they follow like similar engineering pattern. The first, I'm showing an electrostatic discharge event, the ESD. The immediate goal here is for the circuit to survive. So a transient may enter the electrode, or lead or through a feed through or any other exposed interface. So the protection network must limit the voltage and divert the current away from that sensitive circuitry inside. And then there is electrosurgery, which creates a different challenge. Um, it creates high frequency energy that can couple into our sensing paths. The system may not only need protection here, but also filtering, blanking, and also a controlled operating mode and verification that normal behavior returns to after the event occurs. And then we have a most common problem that is magnetic resonance, MRI exposure. In it's much broader than the other two because the complete implanted system may experience more static magnetic field gradients and RF energy. So compatibility depends on device, leads, operating configuration, and a lot more. And the last is the extreme storage temperatures. So we might need to have some internal temperature measurement that may prevent sensitive function from operating until device returns to an applicable range, because we might be burning a lot of power it might be much better off stored for the battery actual use case. So the details here are different, but the sequence is kind of similar. So we recognize the problem, protect the circuit, control the system response, and make sure the system recovers. But none of these are aging tests. They verify the protection and response mechanism and ensure that the device behaves correctly after this extreme conditions. Once these mechanisms are evaluated, the next layer of evidence comes from testing the manufacturing device as it moves forward to production. So here I'm showing a rough production flow. Um, so this can look repetitive. So the device is tested first at a wafer level. It is tested again after packaging. It may be tested again after a stress condition. And then there is a final systems test. So why do we test the same device so many times? The answer is that the device is not really in the same condition at each stage. So at wafer test, we are primarily looking for fabrication defects, any parametric outliers, and we are confirming that our circuit functions as we expect. And after the packaging, there are new failure opportunities. There are now interconnects, package stresses, and possible parametric shifts that can be caused during the assembly of this package. Then we have to perform a pre-stress measurement uh, to have a baseline. The device goes through burn-in afterwards, which is maybe a high temperature soak for like 24 to 48 hours. Uh, and this is a controlled way of stressing the part and accelerating the failures. Afterwards, the selected measurements are repeated again to look at the failures to see if there's any meaningful shift. And see and observe if there's any meaningful shift that might have been accelerated due to this burn-in operation. And then at the end, we have this final functional test. We evaluate the complete product configuration, and we ensure that we calibrate any variation, and we tested our end-to-end operation. So not every test is repeated every time, but some are deliberately carried through the flow. The value is not only with the absolute results, but it lies in the comparison. If the device measurement changed, and when did it change? Uh, is it after fabrication or after packaging? And what is the production flow? Um, Helps us understand. One of the measurement that can be especially informative across these stages, which I might be covering a few of them, is a leakage current or IDDQ. I hope everything is going well. Like, if you have any questions, let me know because uh, it might be like really going through slides. Right? Okay, coming to current and leakage screens. Sorry, there's a lot of information, but there's a lot with reliability. Um, So supply current test is a really powerful test signature because there are many physical defects, changes amount of current we have drawn through the source. A circuit may still produce an expected output and yet draw significantly large amount of current than it is supposed to. That excess current may come from like an oxide defect, um, or some excess junction leakage, a resistive bridge between two nets, like a stuck on device, or another unintended path from supply rails to ground. So current testing can reveal problems that basic functional tests may not immediately expose. But these are important conditions attached. So there are some important conditions attached when I make that statement. So the measurement has to be under some well-defined conditions, right? So it should be in some low power state to even observe these uh, leakage currents. So the current depends on the operating mode of the device. It depends on the state of the device. It depends on what supply voltage and temperature we are using. Um, and a different state might cause like a different uh, current signature. So a circuit measured too early may look like it has excess current when it is still settling. And as normal background leakage becomes longer, a small defect signature can become more difficult to separate from the expected variation. So it's very important to know the condition we are testing it in. And that's where the strength of this test lies, is in the isolation, right? It comes from controlling the condition and making some repeatable measurement that can be compared with some baseline. Um, but this test is still an indication. It tells if the behavior is abnormal, but does not necessarily identify the exact physical root cause of the problem. That usually comes with additional diagnosis. And even a good functional current screening, there are some weaknesses hidden until the device is exposed to various stress events. So next, I want to quickly also cover the reliability stress testing that we have to do, which will reveal any marginal failures and early life defects. Right, a device can pass through its nominal test, but still it can hide some manufacturing defects. The purpose is not sim- here is to make the device work harder, but the purpose is to expose the behavior that the normal test won't reveal to us. So burn-in applies an elevated stress so that the units with latent early life defects are more likely to fail during manufacturing rather than after release. That is why that is why it is associated with early failure defects, and accelerated life testing makes a different question. So we can either do early life defects with a burn-in, or we can also have an accelerated life defect. Instead of asking whether the particular unit is weak, it is examining whether the design or the technology degrades over time. Um, so the stress in this case is increased so that the relevant aging mechanism develops faster than it's under normal operating condition. The exact stress depends on what we're trying to study. It may be a temperature, voltage, mechanical cycling, or some other control variable. But regardless of the test, the measurement sequence is what makes the result meaningful. First, we should establish a baseline and apply the control stress and see and compare the results and see what shifted. And we observe if the device failed, if there's any parametric shift or the margin decreased. Um, because a device may still function after stress, and yet it could have drifted from its specification limit that we measured during the baseline test. That movement uh, be more infor- uh, can be more informative than simple pass-fail test we had during the functional test. So here on the right, you already might know is a bathtub curve that gives us the reliability concept, like a context. But the practical engineering process is sequence uh, given by the baseline measurement, control stress, then post-stress measurements. So together, these the design, qualification, production, and the stressed activities we talked about provide a strong evidence before release. But every additional condition, measurement, and test instruction require more time, equipment development, effort, and data analysis. So we have to ask one practical question: is how much additional tests as we keep on adding can we afford, right? Uh, so because every additional layer we are adding to ensure the assurance of our device and to add confidence, we are adding some kind of additional time and cost. So at a simplified level, a tester cost per test good device depends on effective hourly cost of every equipment we are using. And then it's multiplied by the amount of time a part spends on the tester. So the test equipment cost is mostly fixed. So when we add another measurement and operating condition or another stress event, we are actually increasing the overall test time. And the tester is extremely capable of testing, but it does charge by the hour, right? So we have to make sure that the test time doesn't blow out and ensure that the reliability still we meet our reliability requirements. So there are several techniques we use like multi-site testing. So we can test multiple devices at the same time, and we can do parallel testing of compatible devices and channels. But the embedded test, the main topic of this presentation, can also reduce the amount of external instrumentation and data collection needed. But the embedded test does not come for free. It adds some circuit area, some design effort, and additional verification and more power. So the goal is to not simply to add more tests, but the goal is to identify the measurement that provides the additional confidence that can justify that cost we want to bear. Even when we are willing to pay that for the extensive production testing, there is another limitation. Most of the visibility appears, most of the visibility that we have during these tests disappears as we leave the test environment and enter the field. So we have to talk about the visibility gap we have between the production test and in-field operation to exactly know what we need for the optimal embedded test. So during production test, here we can have created a control condition. We can apply any precise stimulus we need. We can access any test mode, observe any internal node, and investigate any abnormal results. But after deployment, that environment no longer exists, right? We no longer have direct access to most of our internal circuit nodes, and the present tester we relied on is gone. And energy, memory, and any communication bandwidth we have are all limited now. What remains is only um, the observability that we intentionally designed beforehand into the system. That may include some measured code or some current estimate, some timing count, some protection flags, or any stored event or small amount of diagnosis we put into it. So traditional tests can establish that the device met its requirement in the beginning of life, but by itself, it does not tell us whether the performance margin changes throughout the operation. To gain that visibility, a few selected measurements have to move from the external tester into the device itself. That is where the embedded test and reliability monitoring starts to connect with each other. So this diagram here shows the idea at a system level. So the chip still contains the functional blocks we would expect. That is that analog front end, the data converters, the references, clocks, and any therapy, digital logic, and firmware control we need. The difference is that the selected observation and test capabilities are also built into this architecture. A monitor may sense supply current, compare a voltage, count cycles, inject some known uh, signal, and capture the converter's response and verify it against an established baseline. But the analog measurement should not remain uh, as an inaccessible quantity in our design. Wherever practical, it should be converted into a digital format, a code or a count or a signature or a threshold. So it's much easier to actually measure and collect and store. And also, we need not add any additional mixed signal circuitry than needed, right? If we convert our analog signature to a digital format, uh, it saves a lot of burden on the embedded test. Um, the MCU or the digital controller, if you have in your system, that can then schedule the measurements, apply the operating conditions needed, and compare the results to an established baseline. That creates a kind of progression. The embedded test creates a controlled measurement. Reliability monitoring repeats selected measurements over time, looks for meaningful change, and then the diagnostics adds operating context and event history so that the change can be interpreted later. The same uh, so the same internal infrastructure can support a few functions. To make this practical, we usually try to reuse what is already existing within our a chip, like ADCs or DACs, any comparators, counters we already have, and we can reuse the firmware or any telemetry channels we have to convey the information we have actually stored. The objective is not to recreate the full production test inside the chip. It is to preserve that small set of trusted measurements that can tell us whether uh, the behavior is preserved. We can now look at what those embedded measurement might actually be. And one of the direct places to begin is again with the supply current monitoring. So again, circling back to the supply monitoring, one of the most direct quantities we can monitor is the supply current. At a high level, the circuit shown here is an embedded current monitor. Uh, we would not place a separate monitor at an individual uh, device or a circuit. Instead, we have a few selected regulators that can provide visibility to different supply domains and sections of the chip. Um, so a scaled copy of the regulated current can be mirrored into our monitoring path and compared against some established limits. What the current represents depends on how the section is configured. So if clocks are stopped and selected blocks are turned off, the measurement becomes a leakage, like IDDQ. If the sections are placed in a defined state, it becomes, if it's a standby state, it becomes a Quiescent current check. And if the selected functions are enabled, then it becomes an active current read check. So the monitor hardware remains the same, while the firmware changes the operating state and selects the appropriate limits we have to look for. The overall function here is simple. So we measure the section current, compare it with the expected range, and generate the compact result. Um, so during the production test, the monitor can provide a current signature for each selected power domain. That measurement can establish a kind of baseline that we can use and compare it throughout the life. So if the uh, same test is repeated under similar operating condition, the change in that result may indicate some increased leakage or unexpected activity. Um, and we can actually identify that there is something wrong with the implanted device. So the monitor again won't directly give us the exact block or the node that is responsible, but it can show us the signature of a particular section, and which gives a useful starting point for any diagnosis we have to do later. So current monitoring gives us visibility of the power domains. And the next thing we can also try to observe is one level higher and looks where and start looking at the supply level at the battery and the power system of the chip itself. So here the battery and the power domain provides us with three important characteristics that we can measure, right? It can be either the battery voltage or the supply impedance or the battery current. In this example, we use the same ADC for all the three. They're all muxed into the same ADC. So we can use like a small resistor divider that measures the battery voltage. Uh, and when so we can disable that resistor divider when we are not using it, so we don't keep draining the charge, but it can step down the voltage to enough so that it's within our ADC range. And that voltage will provide information about the available operating margin, but voltage alone will not show how well the battery can support any loads we might have. Further, the system can apply some kind of known current load and measure the voltage change, and the ratio should give us the battery impedance. As the impedance increases, the battery may produce more voltage droop during high current activities, even while its resting voltage still appears to be acceptable. And the third measurement, which is very crucial, is battery current. We can use a small sense resistor and a current sense amplifier and allow the system to monitor overall operating current. Um, and especially in a rechargeable system, it's extremely crucial to monitor the rechargeable current so we won't blow up the battery. Uh, so none of these measurement should be taken alone. The temperature, battery chemistry, state of charge, and operating mode all matter for this. But when the measurements are repeated under known conditions and compared with previous behavior, they can provide indicators about abnormal current drain, maybe recharge problems, and any issues with the battery chemistry. Another, so moving on from this, the next embedded system I want to cover is clocks, which are essential for timing. Any questions? I'm just blasting through this, that's why. Okay. So clocks monitoring. So clocks are really easy uh, signal that we can monitor on the embedded monitoring, and these should be present in every implantable system we deploy. Um, so in this example, I have a reference clock that defines a known measurement interval, and during that interval, the system counts the edges from each oscillator under the test. The edge counts provide us a measure of frequency, and the captured clock state provide the duty cycle. The same architecture can support multiple oscillators and return compact digital results into the firmware. Um, it can also help detect startup problems if an oscillator is enabled but does not produce an expected number of edges within the allowed intervals. The system can identify like a slow start or a missing clock. During the production test, the reference may come from the tester or from an external clock on the load board itself. And during operation, um, we need another internal clock or a reference that we might have to use that can be an already present crystal or an internal clock that can be used as a reference. And at this, when we use an internal clock, we are actually looking at the ratio of the frequencies between the clocks, which might be already established. So this provides us with a useful information because any unexpected ratio change can also indicate that one of the clocks has drifted. The Also, we can have a few ring oscillators or timing structures within the chip which are not exactly providing the timing control, but they can act as an indicator as process variation or aging, because their frequency reflects speed um, of underlying devices and timing paths. The main idea is simple. So small amount of digital logic can turn clock behavior into frequency, duty cycle, and startup and any long-term aging or stability information. Um, so we have now looked at power and timing in our last few slides, and the next two slides, we turn to one of the most important mixed signal blocks in acquisition chain, the data converter itself. So we have two different types of data converters that we can have in our implantable systems. So the first thing I'll be covering is a Nyquist ADC and a self-test that we can implement within the chip. So any ADC needs to be sampling at a Nyquist rate, which is at least twice the frequency of the input frequency to make sure that we don't lose the information of the signal. So that's the Nyquist law to anyone who might not be familiar. So these particular ADCs are sampling at a rate just barely more than twice the frequency. So these data converters are important targets for our embedded test because they connect the analog sensing path to the digital system, which is very vital. One of the harder converter properties to evaluate is the linearity of that converter. In conventional test setup, the ADC is driven by a very accurate external signal source that works well, um, but reproducing the same quality of signal on chip will require a lot of area, power, and design effort, which might not be ideal in our case. So this slide is showing one of the principle that's published that is very useful. It's called a user smile approach. So here we take a different approach. Instead of requiring one nearly perfect stimulus, the ADC is tested with two nonlinear but related signals that have a controlled offset. So the ADC converts both these signals, and the two digital data sets are processed together. Because the relationship between the stimuli is known, the algorithm can separate much of the stimulus error from the converter's own linearity error. The important point is that the analog stimulus does not always need to be more accurate than the converter if its error can be identified and removed digitally. That can make the embedded stimulus source smaller, low power, and easy to integrate. Um, and for design and test audience, an additional note is the segmented ADCs um, uh, reduces the number of unknowns and reconstruct ADCs into INL. So the DNL and pass-fail results can then be derived and identified because we have identified the transfer behavior. So the Nyquist converters produce relatively direct output code for each sample. But there is another style of converters we might have in our systems, which are sigma delta converters. They create a different challenge because they're sampling faster and they employ a noise shaping mechanism. Um, and that introduces code variability, which must be dealt in a different way. So for a sigma delta converter, if we provide a fixed input level, so the output does not necessarily remain at a stable one code. Because of any quantization noise and the oversampling itself, the output varies across a known distribution to nearby cores. So I'm showing a MATLAB animation on the slide that shows the behavior directly, that is simulated using a model of a n order sigma delta modulators. The So that variability is expected, and the test architecture therefore should collect enough samples to estimate the converter response reliably, uh, rather than judging it just based on one code. So in this example, um, the same controlled stimulus is applied for multiple converters in parallel. Each converter produces sequence of output codes, and each channel uses a circular buffer to retain the history. The purpose of this buffer is to not store the complete raw output stream indefinitely, but it captures enough code variable data to account uh, for the linearity calculations. So the digital processing after converts the accumulated data into useful information, such as the linearity INL, DNL, or and it can also be a compact pass fail if we already established a baseline. Um, so during the production test, a more complete version can establish that beginning of life linearity, like we talked about. And during the operation, a reduced test can revisit some selected input levels and look at the signature and compare it to the baseline. We have now followed the signal through the power, timing, and also the conversion. And the final thing I'm going to cover in this presentation looks outward at the leads, electrodes, and the tissue path itself. So looking at the lead and therapy path monitoring, the key question here is whether the electrical path from the device to the lead or the electrode is still behaving as expected as time passes, right? The important point is that the therapy delivery and impedance measurement operate um, in some kind of windows. So during normal therapy, the output driver can deliver the programmed stimulus through the output terminals. And during the diagnostic therapy, we can use the same terminals to do some kind of impedance measurement of that electrode. So we can have a separate AC test current um, that can be applied through our output terminals, and the system measures that differential voltage across the terminals, and we can estimate the total terminal impedance from that measured voltage and known test current. That measured value represents the complete path seen after the implant, right? It can include the lead resistance and the electrode to tissue interference, and the tissue interference path, and any return path leakages we have. So the model I'm showing at the bottom is like an illustration of that electrode tissue interference. It's just an example. So it shows us that how complex and frequency dependent it can be. So a high impedance measurement in this monitoring can suggest that we might have an open or a disconnect path, while a low impedance can suggest a short or an insulation issue, right? The same measurement can also be repeated across several frequencies if you want to create a Z-gram that provides a much richer view of frequency dependent behavior of the electrode and the tissue path. But the greatest value often comes from looking at the trending, right? Comparing it to an actual previous behavior. So a single measurement gives us a snapshot. So repeated measurements can reveal like the gradual degradation or changes in the lead and the electrode to tissue interference before we even develop any clear open or shorts. So across all these examples, the pattern is similar. We create a control condition, make a compact embedded measurement system, convert it into some kind of digital result, and compare it with the device baseline that we measured during the beginning of life. So that brings us to the next question. How can calibration and beginning of life baselines make these compact embedded system useful without over designing every measurement block? Right. So this one. So here I want to quickly cover uh, the baseline and calibration techniques we must be employing. So compact embedded instruments that we are employing within the chip is not necessarily laboratory grade or the test grade, right? In many cases, they don't have to be. We should not expect every current monitor or a threshold DAC or the counter or an impedance measurement path provide us the measurement with absolute accuracy. So we can use production calibration and remove a lot of systemic errors like offset, gain errors, and threshold mismatch. And the calibration becomes a really powerful tool here. So a beginning of life measurement can establish how the particular device behaves under defined operating condition, and later measurements can be compared with the original value rather than against like a population-wide specification that we establish. This is important because device to device variation may be completely normal. What may be meaningful is whether one device has changed significantly from its original established behavior. Um, of course, the comparison comes with its own flaws because temperature, supply conditions, operating modes, and the measurement configuration should be exactly similar, or their effects should be accounted for. So the embedded instruments need enough repeatability, calibration, and context to detect meaningful change. This makes it possible to use smaller and low power measurement resources without over designing every instrument we put in. And those measurements can remain valuable beyond their immediate in-field use, right? These are not just used to just ensure the device has seen any shift, but they can also preserve valuable information that can be used later, especially when the devices return for failure analysis for some damage. So here the embedded measurements value the systems we are putting in have value beyond in-field monitoring because they can support diagnosis and field return analysis. So embedded measurements can also, at production tests, calibration and characterization establish uh, a beginning of life baseline for individual devices. And during operations, a selected measurements can be repeated and stored over time. And this may include current signatures or some supply monitoring or clock measurements or any lead impedance measurements. If an abnormal event occurs, an alert can be generated or the device can be later returned. And those earlier measurements can provide evidence that would otherwise be unavailable once we get the device back. So this is important because the condition that caused the problem may have developed gradually, appeared intermittently, or disappeared by time the device reaches the laboratory, right? So return device often shows us only the present state of the device. So the stored history may help us show what changed before that event actually occurred. Um, the history may, for example, the history may show a sudden increase in current or a rising battery impedance or a converter drift or an impedance change. But none of these observation necessarily identifies the root cause itself. Um, but they provide a small piece of information that we can use during variant analysis to build a bigger picture. And it'll also help the failure analysis team in the future to narrow down the issue. This as the systems become more intelligent and highly integrated. So the practical takeaway here is embedded monitors may not identify the root cause directly, but they can preserve evidence. But as the systems become more intelligent and become more integrated, this kind of observability becomes more valuable, but also it is difficult to preserve as we try to make our systems more compact and more smarter with our algorithms. So that brings us to the future section of our topic. Eric, can I get a time check? Just want to make sure.
We're basically only have like 1 minute left, so go quickly.
Oh, quickly, yes. I have like 3 slides left. I want to cover like what kind of integration challenges we have in the future. So our biomedical systems usually adopt any change deliberately because it's understandable because we rely on safety, reliability. We have long product lifetime and validation processes. So we have a threshold for how much change we can adopt. But broader direction of electronics can give us a picture of where we are headed. So uh, we started from distributed electronics. Um, where we had great relative physical access for test and debug. And then we moved to system on chip, which brought many functions onto one die, but we reduced the size and interconnects, but we started hiding some of our internal nodes, and it's hard to access that we were once easily accessing at broad level. And then in future, we might head to the system like a system in package, where integration of analog digital memory uh, and several of these functions use different technologies um, for each function. And also it can be advanced to this advanced packagings that we are seeing, like 3D packaging or 2.5D, that can increase the density much further, which can help with the battery life. But these approaches also bring some real issues with observability. So I'm showing a small trend at the bottom, which are opposing. So this shows that as the integration increases, the direct physical test access generally decreases. So in a distributed system, external equipment may provide much required visibility, but in a highly integrated system, more visibility has to be created internally through test access and embedded instruments like we talked about. So the baseline takeaway here is more integration demands more built-in observability. So these advanced integration will come with new challenges, and we have to solve them. So I'm just quickly showing like three representative areas that are challenges. One is the increasing memory when we especially adapt like some kind of AI or machine learning algorithm styles. And then we can have hidden interfaces if we go to advanced packaging. And obviously we need more embedded health monitoring to detect these issues. So for memory, the built-in self-test can detect faulty cells, rows, and columns, and we can have some kind of mechanisms to test our interfaces, like die-to-die interconnects, package traces, using some loop-back tests and boundary checks that are all available in publication. Sorry, I'm rushing because of the time. Um, and also it becomes more vital to have these embedded instruments we're talking about to measure voltage, current, timing, all the signatures we are talking about. And it is more critical than ever to have these if we want to see ourselves adapt these new technologies in the future. So this I just want to show that how this planning doesn't happen after the release. This has to happen way before the release, right at the planning stage. So we have to define the test access, we have to place our monitors, we have to plan redundancy, we have to include the firmware or any scheduling or modes we want to include within, and we have to verify the test and also have some repair mechanism built in to have some redundancy. So the bottom line is observability cannot be added after the access has already been lost. So coming to the end, the key takeaways is just recapping is reliability begins with sound design, qualification, production tests, stress testing, and system verification. And embedded test does not replace those activities. Uh, its value is that it extends selected observability beyond manufacturing when the direct test access is no longer available. Um, we looked at several examples like current battery, clock, data converters, and lead impedance monitoring. Each measurement provides only part of the picture. Its value increases when it's calibrated, repeated under known conditions, and compared with the baselines we established. Then the stored signature and trends can also preserve evidence for diagnosis in field analysis. They may not reveal the root cause directly, but they will show what changed and help us narrow the investigation. And also, we looked at as integration keeps increasing, the physical access keeps decreasing. So built-in self-test or monitoring redundancy and repair are becoming way more important than ever. And these capabilities cannot be added effectively after the design phase ends. So at the end, the embedded test is not the reliability strategy itself is an additional layer for visibility evidence that can help preserve confidence throughout the device lifecycle. And that ends my presentation. And if you're interested in any of these topics, I have references at the end if you would like to go and have additional reads to dive deeper. Yeah, thank you. Sorry
Thank
about
you.
time. It was
Thank you,
rushed.
Krishna.
Yeah.
Yeah, we're kind of out of time, but we'll see if there's any questions. Quick question is,
Yes.
Krishna, can you send a PDF of this that we can make available to the people?
Yes, I will do that.
Okay. Looks like we have some questions.
Okay.
I don't know if you can read the chat room at the same time,
I
but
can. I
hello
can try.
from Guatemala, Alan. I'm an
Oh.
electronic engineering student with a strong interest in mixed signal. What tools or software should I start exploring now to better prepare for a master's or PhD in medical mixed signal design?
I don't know if the question is exactly for if you're focusing on electronics or medical design in particular. So the tools are usually EDA tools, which might be very expensive sometimes to get a license, but the universities usually have free licenses. Uh, so we do use several EDA tools like Cadence and um, uh, Synopsys. But another important tool is using some kind of simulation environment. Like we use MATLAB, but that's also expensive for licensing. But you can also use any simple Python coding, but it takes you to another route. So it's a tough question to answer. So if you have access to these tools, I would say you need access to some of the EDA tools if you're talking about design in particular. Any inputs, Andy, on this? You might have more experience. I don't know if Andy's online still, but
He said thank you. Alan said thank you very much. And I don't know
okay.
If Andy was able to unmute himself, but Alan,
Yeah.
thank you. Yeah. Other questions from anybody else? While they were thinking about other questions, Krishna, are there any, going off a variation of Alan's question, are there any reliability modeling tools for the integrated circuits that you work on? Oh, Daniel has a question.
Okay. For your question, I learned most of the reliability challenges after the school, right? After actually working on the product itself. Yes, there are reliability models that are managed by the reliability team itself. We have extensive studies. I'm sure you worked out with your DRM,
Okay, very good.
with Metronic a lot, right? So those
Yeah,
are the tools that we need.
thank you.
Uh, yeah.
Yeah, Daniel has raised his hand. Daniel, can you either unmute yourself or put in the chat room?
Krishna, am I audible for
Yes,
you?
Yes.
you are.
Excellent. Great presentation. I have a question for you on the repair part
Yes.
because you say it twice here in this key takeaways,
Yes.
but I'm not sure I saw how you might repair in the existing system. Are you talking about future capabilities for repair, or was there some sort of built-in repair in the existing system?
So existing systems didn't have it because uh, this is mostly based on how we are headed to the future, into the future. The most unreliable parts come from where if we sync our process nodes, right? So if we move on our algorithms into a more machine learning based, which can give us more reliable outputs, we might end up having more memory at lower process nodes. That's where repair comes more vital. So you need a way to have a built-in self-test, and you need redundancy to replace the failed uh, cells with new cells. And also, even in packaging, right? When we go to this advanced packaging, they will give us a compact form factor and more life to uh, the the device itself. But it comes with a challenge where these interconnects are usually through silicon vias that are being built, which are really not reliable again. So you might have shorts or opens. So it's essential to we have a mechanism to test our interconnects. So we have some kind of systems between the
Right.
pads that can talk and some redundancy to change the path, right?
So,
So those are the
Chris,
things. Yeah,
and one question, maybe it's a little
yeah,
bit sensitive, but when
yes.
you, how do you get them back? I mean, they've been inside a person. Is there, is it as fast as like a bottle return fee that if you
No.
send it back, I mean, how does this happen?
So usually the issue is identified at the clinic or wherever they are, and sometimes even though it's horrible, we try to fix things with just a firmware patch if possible. But if it's not, we have to explain the device, and there is another regulatory procedure for that. It's a whole another level. We have to resolve the issue within, identify
Yeah,
the issue and resolve within a time.
that makes sense.
Yeah,
Thank you very much
yeah,
for, yes, thank you for your
yes, yeah,
presentation.
I do have a
Go ahead,
question,
Christian.
yes,
Krishna.
Christian. Yes.
before I ask this very good presentation, I really like how you integrate the technical and non-technical stuff here. Why do we do reliability, especially
Yeah.
medical devices, right? Just one thing, uh, we are actually leading the IEEE 1856.1, which is the
Mm.
prognostic health management.
Okay.
If you have some feedback on, repairable devices, let me know. Send it my way. We're,
Oh, definitely. Yeah. I will.
making that standard.
Yes.
Also, I think I know the answer to this, but for the team here is we are in I work in microchip. We are in your what do you call this? We are your suppliers.
Yeah.
When selecting suppliers, or monitor, do you require a specific standard, specifications, or monitoring?
Yes. Usually, we do have like we might have a narrowed limit. Or correct me if I'm wrong, because I'm coming from the design side, I might not have exposure. You can also give. So as I know, like yeah, every component we buy, we do have a separate specification and limits that it has to fit in, and also extensive testing or flows it has to go through if needed before we select a product. Do you have any additional inputs?
And
Yeah.
that you're hitting exactly the point,
Yeah.
Krishna. And one thing that because some of our suppliers here are
Yeah.
or customers, my side, right? Customers now,
Yes.
medical devices. Sometimes they require a specific, let's say, burn-in condition, like what you said. Hey,
Mm.
before you
Yes.
sell it to us, make sure that it is burn-in, because let's say it goes to the heart of the patient, right? So it's a
Yes.
high-risk devices. So
Yeah.
yeah,
But it's funny because again, we might do the same test actually.
exactly.
So, but yeah, but
That's
it
why
is
it's like,
required. Yeah.
that's why I'm pushing Y, right? For some of the stuff.
Yeah, but this is like a big uh, issue, like ongoing issues. Burn-in is how do we determine how long we have to or where we have to. I know we have some models that tell us how long it has to be, but it takes a lot of time and money to go through this. So
Yeah,
yeah, that's a good research topic if anyone like want to explore it. So right.
Krishna, thank you, sir.
All right, thanks. Any other questions? Well, thanks. We went over a bit, but I could have a chance for some questions. And thank you very much for your really good insights, Krishna, and thanks for those great questions. Have a wonderful rest of the day, and happy Independence Day. Happy 4th of July, everybody.
Yeah. Thank you, everyone. Yeah.
Thank
Thank
you.
you. Cheers.
Well, this presentation was recorded, so we'll have it posted in the near future. Take care. Good job, Krishna. Thanks.
No, thanks, Eric. Yeah. I know it was a lot packed into one, but
A lot. All right, take care.
yeah, thank you. Bye.